Good morning everyone, I'm Winnie Ng from Maths 3. Today, I'm going to present about the application of vectors in navigation field. First of all, what is vector? Actually, vector is a mathematical tool to represent direction and magnitude simultaneously. According to Berthold and Morrison, vectors navigators are thought to have a precision of direction and thus maintain a consistent average direction regardless if they are physically displaced to new locations. These vectors are essential in analyzing the movements of vehicles, aircrafts, and ships, ensuring precise route planning and necessary course adjustment. By applying vector principles, navigator can effectively counteract external influence such as wind and ocean currents, thereby improving travel efficiency and accuracy. In today's fast pace, modern navigation systems integrate these vector calculations in real time, providing continuous updates to ensure safe and efficient travel across various modes of transportation. Next, we are going to look for the application of vectors in navigation field. First, maritime navigation. Maritime navigation has significantly advanced with vector mathematics, particularly in course plotting and position determination. Vectors help navigators by combining a ship's intended path with external force like wind and ocean currents. By representing speed and direction as vectors and adding them together, navigators determine the vessel's true path, making necessary course corrections to ensure safety and schedule adherence. To enhance this process, bidirectional long short-term memory (BILSTM) networks, a type of recurrent neural network (RNN), have become essential for predicting ship movements and optimizing routes. According to Shi et al. 2025, it is designed to handle sequence data and capture long-range dependencies. BILSTM processes navigational data in both forward and backward directions, improving trajectory predictions, collision avoidance, and fuel efficiency. These networks analyze vector-based representations of complex movement patterns, influenced by environmental factors, enabling smarter, real-time decision-making. With BILSTM integrated into vector-based navigation, autonomous maritime transport is becoming safer and more efficient, revolutionizing how ships operate in dynamic ocean conditions. The figure shows the input features of BILSTM. Next, Global Positioning Systems (GPS). In GPS systems, the signals from satellites are processed as vectors, where the vector's length represents the range and its direction indicates movement that allows for the accurate computation of a receiver's position. This vector-based approach not only improves the accuracy of position fixes by effectively managing errors that caused by signal attenuation and multipath interference, but also enhance the robustness to disturbance of navigation systems in dynamic environments. For instance, vector tracking loops (VTLS) have been effectively applied in pseudolink navigation systems to overcome the near-far problem, thereby expanding coverage in indoor and urban canyon areas. Additionally, the use of vector-based GNSS receivers in autonomous vehicles navigation has shown significant improvement in maintaining accurate position and velocity estimates, even under poor signal conditions. As reported by Ilham Ravi et al. 2020, the vector-based receiver maintained an outstanding navigation solution despite the attenuated satellite. These developments highlight the potential of vector processing techniques as a key enabler for next-generation navigation systems. The first figure shows the navigation solution of the scalar and vector-based receivers compared to the reference baseline on Google Earth. The figure illustrates that the vector-based receiver maintained an outstanding navigation solution despite the attenuated satellite. Similarly, the second figure shows that the velocity estimate of the vector-based receiver was more accurate compared to those of the scalar-based receiver, especially during the time interval at which PRN1 was attenuated. Apart from that, unmanned aerial vehicles (UAVs) are also one of the applications of the vectors in navigation field. Vectors play a crucial role in UAV navigation, providing the mathematical foundation for computing position, velocity, and altitude. UAVs rely on vector-based calculations to maintain stable and accurate flight control by continuously processing real-time data from inertial measurement units (IMUs) and GPS. Techniques such as the wind triangle, which synthesizes airspeed and wind vectors, help determine ground speed and heading for precise course corrections. Additionally, vector field approach divide the planned flight route into convergence and circular components, allowing UAV to correct lateral errors and mitigate disturbance such as winds. Advanced control systems such as proportional integral derivative (PID) controllers improve flight stability by dynamically altering the UAV course. These vector-based computations are essential for collision avoidance, path optimizations, and real-time obstacle avoidance, assuring minimal departure from the intended route while increasing mission efficiency and safety. Now, let's move to problem-solving question. This question shows a cargo ship departs from Port Klang heading towards Kota Kinabalu. The ship's engine propels it at a velocity of 13 knots due east. However, a strong ocean current flows at 8 knots towards the southeast 145 degrees from the north. The diagram below shows the cargo ship departing from Port Klang to Kota Kinabalu. The question states that due to the influence of the ocean current, the ship does not travel exactly eastward. Calculate A. The actual velocity, which includes magnitude and direction of the ship relative to the water. B. Based on the resultant velocity, determine the time taken in hours for the ship to reach a point 250 nautical miles directly east of its starting position, and provide an interpretation for the results. In question A, it is given that ship's velocity is 30 knots due east. Ocean current velocity is 8 knots at 145 degrees from the north. Each velocity is broken into horizontal and vertical components. Velocity of the horizontal component, v1, is v cosine theta, and velocity of the vertical component, v2, is v sine theta. For the ship's velocity, its horizontal component is 30 knots, and its vertical component is 0 knots. So, we write the answer in the vector form, in which its velocity is 30, 0. For the ocean current velocity, the current flows at 145 degrees from north, which is equivalent to 35 degrees south of east. This means that we should use the formula that shown above to find the answer. So, V is 8 cos 135 degree and negative 8 sine 35 degree. The vertical component is negative because it is in southward. Cosine 35 degree multiplied become 0.8192, while sine 35 degree becomes 0.5736, and we multiply them with the velocity. Finally, we know that velocity of the ocean currents is 6.554 and negative 4.589 knots. Then, we compute the resultant velocity of ship and water current. As we know, the velocity of ship is 30 knots, and the velocity of water current is 6.554 negative 4.589 knots. After we sum up everything, we will get the answer of the resultant velocity, which is 36.554 negative 4.589 knots. Next, we calculate magnitude of resultant velocity. We can use the formula of Pythagorean theorem. After doing all the calculation here, we will know that the magnitude of the resultant velocity is 36.841 knots. Next, we should find the actual direction of the resultant velocity by using tangent functions. As we know, tangent theta equals to opposite over adjacent, means vertical component over horizontal component. We change the position of the tangent to the right-hand side and substitute all the values into the equation. At last, we will get the answer, which is negative 7.16 degrees. Since the y component is negative, the direction is 7.16 south of east. Next, we find the bearing of the ship. Since the ship was originally moving due east, means 90 degrees. The current pushes it slightly northward. So, to find the bearing, we use 90 degrees to add the angle south of the east. And we know the answer is 100.73 degrees. Finally, we solve this question by knowing the actual velocity of the ship is 36.841 knots in the direction of 100.73 degrees from the north. Now, we come to question B. In this question, we can consider the eastward component of the resultant velocity, which is 36.55 knots. Given that the eastward distance is 250 nautical miles, and the ship's eastward velocity components is 36.55 knots. So, we can use the formula of velocity to find it. As we know that velocity is equals to distance over time. Since we need to find the time, so let the time become the subject. T is equals to distance over velocity. By substituting the values, we know that it takes 6.84 hours to reach the point. Since the question wants us to interpret the results, the answer will be the ship takes approximately 6.84 hours to reach a point 215 nautical miles east. To summarize, vectors are essential in navigation because they help determine directions and movement with accuracy. Whether for ships, aircrafts, and vehicles, vectors ensure efficient route planning and allow navigators to make necessary course adjustments. By applying vector principles, they can counteract natural forces like wind and ocean currents, making travel smoother and safer. Today's navigation system rely on real-time vector calculation, helping pilots, sailors, and drivers to make better decisions. As technology continues to advance, the role of vectors in navigation will become even more important, improving the way that we travel and explore the world. So this is my reference. It is the end of my presentation, and after this, I hope you can understand about the applications of vectors in navigation field. Thank you for listening and bye!